Well, here we go. We're going to go into Chapter 9 now. So aren't we progressing well? Chapter 9, and we're going to start with symmetry. We recognize symmetry when we see it. Some of the most beautiful forms in nature appeal to us because of their symmetry. We're going to think about it mathematically. We're going to learn definitions of symmetry. What is symmetry with respect to an axis? What axis would we be talking about? Well, for us, we're going to be talking about x and y, the x-axis and the y-axis. We're thinking of the Cartesian plane that you have been studying for all these years. And when we test for symmetry with respect to the origin, we're thinking about that point on the axis that's 0 for x. So here's x, 0 for x, and 0 for y. So we're talking about right here. We're going to also learn whether a function is even or odd. Please don't say who cares. We actually can use that information to help us out when we are graphing. In the end here, we'll be able to graph any quadratic function. So let's get started with this. Oh, before we do, one of the things we know about quadratic functions, how do they graph? They graph like this, don't they? And one of the things we know about quadratic functions is that they are symmetrical. And their axis of symmetry goes right through wherever their vertex is, right? So the axis of symmetry goes through their vertex. At some point we're going to be, I'm not sure if it's today or later on, we're going to be thinking about quadratics that graph like this. These, however, are not functions. Perhaps you can tell me why we do not consider these to be functions and yet these are. Well, we can draw a vertical line anywhere on a function, the whole domain, and we will only see it pass through the graph once. That's a definition, really, of a function. For any x value, there is only one y value. In the case of this parabola, I'm okay up to the vertex, and as soon as I start moving into that parabola, it fails. It is not a function. But at some point we'll be talking about those. Won't be today. It'll be, I think it's in chapter 10 we'll be talking about that. Okay, we're going to go ahead. Remember, this first part is just a little review. If you feel you don't need it, just skip right over it. It usually does take us about 5 minutes to get through it. We're going to evaluate both the function f and the function g. Please remember that this is functional notation. It is telling you that we are talking about a function. It does not mean multiplication. And I'm so sorry about that, because we've trained you for years to see something like this as multiplication. No, it's not. It's saying function f. We could have written it this way. Y equals x squared and y equals x to the third. But you can see there's a problem. We're using the same letter y to represent two different functions. I could say y sub 1, I suppose, but in mathematics, that usually means a specific value of y. So what we do is, rather than get into this complication, we say instead of writing y, although this will represent y on the graph, we're going to say function f whose input is x. And this one will say function g whose input is x. So all this x means here is, what am I putting into the function? And over here on this side, we see what the function does to that input. We have an input of x, and what are we doing to it? Squaring it. We have a function g, and what are we doing to that input? Cubing it. All right. So this function, when we put in x is 2, that's our input, it's going to be squared. My result would be 4. And if I put in x equals negative 2, my result would still be 4. Over here for this one, if my input, instead of being x, I put in 2, 2, and I cube it, what am I going to get for an output? Cubing it, that's 2 times 2 times 2, that's right, we get an 8. And if I put in a negative 2, what will I get then? A negative 8. So you notice something here, don't you? When you had an even exponent, it didn't matter whether you were using a positive or negative, you got the same output, 4, a positive 4. But when you had an odd, so this one's odd, and this is always true too, when it's odd, you can have both a positive and a negative depending on what you are putting in. If you put in a positive, you get a positive out. If you put in a negative 2 coming in here, we cube it, we come out with a negative 8. Well, let's try that. We'll get a little more obscure with this. If I have function f, and instead of using x, I'm going to use a. So that's going to be my input now. I'll have, instead of x, I've got a to the 4th. And for g, let's try g at the same time. Instead of putting in an x, I'm going to put in an a. And what does this function do to an a? What does it do to every input it gets? It takes it to the 5th power, so that'll be a to the 5th power. So function a, function f of a is going to be a to the 4th. And function g of a is going to be a to the 5th. That seemed straightforward enough. All right, so we just did this one. Now we want to try it with a negative a. Function f, if I put in a negative a instead of an x, function f is a raises your input, putting in negative a, raising it to the power of 4. Oh, this is interesting, isn't it? Because I could look at this as, maybe it'll help, a negative 1 times, it's supposed to be a little times marker, a positive a. I could do it that way, right? And then I could distribute my 4 to the coefficient and to the variable. I would have negative 1 raised to the 4th power and a raised to the 4th power. What's going to happen here with my negative 1 to the 4th power? We'll try it right now. Negative 1 times negative 1 gives you positive 1. Times negative 1, that's right, negative 1. Times negative 1 again, that's your 4th one. And you're back to a positive 1. So it's a positive a to the 4th. Well, when we try g, which is going to take that negative a, and what does g do? What is its operation? It raises it to an odd power. So we're going to take a positive a, raise it, oh, excuse me, a negative a, what am I saying? Negative a, I'm sorry, it's so messy, raised to a 5th power, which is the same as saying negative 1 raised to the 5th power and a raised to the 5th power. All I did there was pull apart the coefficient. The coefficient is a negative 1. We don't usually write it out, but I'm writing it out now, trying to make it a little more obvious to you what's going on. If I raise negative 1 to the 5th power, what do I get? That's right, we end up with a negative 1 a to the 5th, which is equal to negative a to the 5th. Interesting, isn't it? So this was an even exponent, and this was an odd exponent. The even exponent made it so it didn't matter whether I put in a positive a or a negative a, I still got the same answer. Right here it is. Whether I put in a positive or a negative with an even function, it came out the same. With an odd exponent, look what happened. If I put in a positive a, I got a positive a to the 5th. But if I put in a negative a, my output was changed. Now it was negative a to the 5th. I hope you actually stayed with me on this, because this will help you along. It did take more time than I expected, though. I'm sorry about that. Let's talk about symmetry with respect to a line. You could think of it as a reflection. If I take this line and I think of it over this spider, that's the line of symmetry for a spider. Now we know in nature things aren't ever exactly symmetrical. I mean, if we looked at our faces, which we perceive as symmetrical, we'd find they're not exactly symmetrical, but more or less symmetrical. And the line of symmetry would be right here along the spider's body. Gee, I just thought of it now. I hope none of you are freaked out by spiders. I'm not. They're one of my favorites. I always think of Charlotte. Okay, here's another one where we're going to talk about reflection with respect, symmetry with respect to a line, and think about it as reflection. If this represented some sort of a mirror, and we have a line of symmetry right here, what do we expect to see right here where it says reflection? Is that what you were expecting? Now let's do it with respect to a line. Again, only we'll do it with some points that are graphed here. In fact, let me draw this. You know what this looks like, right? I'm not doing a very smooth graph, but it should look more like that. I don't know. I do it worse every time I do it, so I'm going to forget about it. But this would look like a parabola that had been laid on its side. And the line or axis of symmetry, if I did put a parabola on its side like that, would be right here. I can get those dots out of the way. And you can see, maybe I'll change colors here, that the dots exactly match on the other side. What do I mean by exactly match? Well, this one is 1 unit away if we consider these grids as 1 by 1s. This dot is 1 unit away from the line of symmetry, and this one is also 1 unit away from the line of symmetry. Please be aware that anytime we are measuring the distance to a dot, to a point from a line, we always measure it perpendicular from that line. So this grid makes a lot of sense for us. This point, which is 2 units away from the axis of symmetry, is matched by this one, a reflection, which is also 2 units away, and we could see that all the way down that graph. Now this is a parabola that would be a function. It would be, let's call it function f, and its input is going to be an x. And what are we doing to x? With every parabola, we are squaring x. In this case, I'm going to be subtracting 1, 2, 3, 4, 5, 6, 7. We'll learn more about this in the future, how you can figure out the equation like this. Let me change my pen color. So I've got a parabola. I'll try to draw it. I need to practice my drawing. So there's a parabola, more or less. You might be able to draw it much cleaner than I have. And then I've got a reflection across this line of symmetry. Well, don't tell me these are all individuals. Yeah, they are. So there's a reflection. And you'll notice now our line of symmetry is vertical, and we're going to measure perpendicular to it. So let me take this one here. Perpendicular to my line of symmetry, 2 units. Perpendicular to my line of symmetry, 2 units. And this is a perfect reflection across that line of symmetry. So we can have a line of symmetry which is horizontal, or like we have here, vertical. Oh, I can't even draw a vertical line. I have to try it again, sorry. Oh, what a waste of your time. All right, here we go. Where is the line of symmetry for a circle? Now you do have to think three-dimensionally here, because the line of symmetry for a circle would be right there. Well, that doesn't look like a line, right? You know that's not a line. However, if you pictured that as you're looking at the end of a line that's coming straight at you, that's what I mean by thinking three-dimensionally. So you've got this, which is on a flat surface, and then this line which is popping out at you. Oh, I always love this question. Which capital letters have an axis of symmetry? Now I want you to write these down, and when you come in, show me what capital letters you found that had an axis of symmetry. Remember what that means. That means that there's a line that goes down the middle of them, and they are perfectly the same on either side of that. That is, they're a reflection of each other. Now, let's just start with A. I'll get you started. A. Now, its line of symmetry would be where? It's going to have a vertical line of symmetry, which goes right down here, and if I had drawn it better, you would see that that is properly drawn. That is a letter which has an axis of symmetry, a vertical axis of symmetry. Please do not limit yourself to the vertical axis of symmetry. I'm going to let you pause here and work on this one, and I'll be right back. Okay, the axis of symmetry for just 2 points. Well, that sounds pretty boring, but let's try it. 2 points. A nice thing about it, it may be boring, but at least it should be simple. 2. All right, so we're going to see this as 1 by 1 grid, so I'm going to go over one, over another one. That's my point for x equals 2, and then y equals 0. So here's my point. Oh, please. Here's my point right here. And then this one is -2, and y is equal to 0. So where would my axis of symmetry be? Remember, we always measure perpendicularly, so it's going to have to be this line right here. That should be showing up right on the y-axis, and if we measured perpendicularly, we'd find that's 2, and if we measured this perpendicularly, we'd find that's also 2 units away. So the answer to this one would be x equals 0. Remember that x equals 0 is the y-axis. And later on, you may have reason to want to remember that y equals 0 That's right. You know, I'm never going to be getting through this in half an hour. So let me just check this out. We might have to do this in two segments. Yeah, I'm going to go, let's see, altogether I have 16. So let me get through 8 and we'll stop and you can pick it up tomorrow, okay? Sorry. Probably would like to finish it today, but that's going to be, I'm going too slowly, that's all. I don't know, digressing or something. Okay, symmetry. Let's think about this one. We've got 2 points that are symmetric with respect to the x-axis. Okay, let's go back a moment. Here are 2 points which are symmetric with respect to the y-axis. All right, let me start on another one then. 2 points that are symmetric to the y-axis. Let's start there because that's what we were just looking at when we had a, what were those 2 points we had? We had 2 and 0 and -2 and 0. 2, that was right there, 0, and -2, 0. And we had, oh, how terrible. But anyway, that's x equals 0. That was the line of symmetry. 2 points are symmetric with respect to the y-axis, and we said we knew that this was the y-axis. Okay. If and only if, okay, their x-coordinates are additive inverses. Whew, let's stop right there. Do you remember what an additive inverse is? Sure you do. That's all you're doing is changing the sign. So if I have a 5 and I ask you for the additive inverse of that, you tell me -5. If I had a -4 and I asked you for the additive inverse of that, you would tell me 4. So it's simply the number with the opposite sign on it. Same number, opposite sign. So what are the two conditions here? Their x-coordinates, here's my x-coordinate on one point, and here's my x-coordinate on the other point. Their x-coordinates are additive inverses, 2 and -2. So this is true, and they have the same y-coordinates. Okay, so let's look at our y-coordinates. 0 and 0. So we could use this rule. We wouldn't even have to graph. We could just look at the 2 points. We'd see that the x coordinates are additive inverses and the y coordinates are exactly the same. In this case, they were 0. However, I could have had these points. Oh, maybe I can just plain old move this. Just a moment. Let's see how clever I can be. Probably not too. Wait a second. Oh, maybe I can be. Well, no. Okay, here we go. This is pretty clever, don't you think? So those points could have been right there. Let me try describing those. That would be still a -2 and something, and a +2 and something. In this case, that something is 4 and 4. So they have the same y coordinates, and their x coordinates are additive inverses. Now you can imagine if we go up to this one where we want to talk about 2 points that are symmetric to the x-axis. Y = 0 is the x-axis right here. Only if and only if their y coordinates. Okay, so here's a y coordinate. Ooh, come on. So and get these both in here. So I've got a y coordinate of 3. Their y coordinates are additive inverses. So what does my other y coordinate have to be? It has to be the additive inverse of that, a -3. Now I already know that the x coordinates have to be exactly the same, so you notice I already rigged that. And they have the same x coordinates, and in this case I made the x coordinates 1. So yes, these 2 points are symmetric with respect to the x-axis because their y coordinates are additive inverses and their x coordinates are identical. So let's see what page I'm on now. Is it time to give you a break? Indeed it is. We're at 29 minutes. So have a good evening.